I'll be starting in a sec. Unable to pin. Oh. Okay. Let me tweet out that I'm live real quick. Morning, Kakalak Joe. Oh, we have an ad break in 2 minutes and 50 seconds or something anyway, so... Which is good, because I'm not really prepared to start just yet. It's just a bit late today. As usual. Okay, this seems to be running, right? What about you? Yeah, you are running. Okay. Yeah, so I'm not going to start with explanations of what I want to do, just because there will be an ad in like 1 minute or so. So I'm just going to continue what I was doing before without much explanation. It's still the syntax tree, so I'm just making massive changes to it. I basically broke everything again. But I simplified it a lot, I think. There's just one last component I need to deal with. So I'm going to have to think about that while the ads are running. And then we can kind of officially start, I suppose. Okay. Okay. Well, this is not quite right, is it? Okay, so the ad break should be over. So goal for today is to finish up Alpha 4 of the GameBoy assembler. Sorry, my head. So Alpha 4, I finally have like milestones, right? So Alpha 4 is, oh, keyword gen should not be in here. I don't care about keyword gen at all. Hang on. And this one should be next. Okay. Okay, this I might potentially even close. So Alpha 4 of the assembler is nothing really exciting, but we kind of managed to do a syntax tree, right? Although I'm in the process of simplifying it at the moment even more. I'll show you in a second what I did. And all I want from Alpha 4 is basically to open an assembly file and then create a syntax tree for every line, and then just print that syntax tree out onto the console as an output. That way, I can then kind of try and, verify whether the output makes sense or not. And then Alpha 5, or VNext, or whatever you want to call it, but it's probably just going to be Alpha 5, will then be taking the syntax tree and trying to finally do code generation and making sense out of the syntax tree. And that will be where we report syntax errors and stuff. So that is basically it. I have to add this stuff with the symbol tables right here, so add new labels, because that was a functionality that was there in Alpha 3, and then I removed it in between because of the refactor again. It seems kind of weird to remove features that were there before between alpha versions, but I don't know. Maybe I just remove it. We'll see. We'll see how I feel today. We'll see how far I get along, actually. That is the more important bit, right? Okay, so one thing I changed. Don't look at the unary operator at the moment because this is work in progress. This is the one I'm currently working on. But essentially, as you can see with the expression node leave, I have taken out all the error reportings and the generation of the invalid nodes, right? The only invalid node I have now is if I already have an invalid token. So it means while we had the token parsing, we recognized, hey, this is a malformed token. It's like, this is not valid. Absolutely not. We're just going to report that. And then we just attach an invalid node for that. So if we then, when we walk the expression tree or pass the expression tree and we encounter an invalid node, we can just stop trying to make sense of the syntax, right? Which is fine. But I try to okay, well, this makes no sense. I was trying to do a few things. I try to make sense of overall parsing of operands and operators and all this kind of stuff, and I ended up with a lot of the same errors over and over, right? Like all of this, look at this, right? So every single thing, and then every single thing returns an invalid node, and suddenly you have to think about, oh, what do you do with an invalid node once you actually get it? And it kind of became a lot hard to think about all the different situations. And we even saw in the last stream that I already missed a node or a token, right? And then we got kind of stuck in this infinite loop where it was just trying to parse expressions forever and ever and ever, yeah, right? So it's not really a good thing. So Now instead what I'm doing is I just build the tree with whatever I'm getting, and I don't care whether it's malformed or not, right? So if I get a register, I just add a register node. If I get a directive, even though a directive should not be in an expression, I just attach in a directive node, right? Because it's not job of the tree builder to actually verify that the tree is correct. That will be done in the parsing. Same with like labels and stuff like that. And all of this, so this is basically the meat of everything. Like this is the whole parsing, right? And then it's just basically different nodes that I'm attaching. Now, of course, there is some things to watch out for. For example, unary operators I'm just working on. But for example, binary operators, right? So you might think, what if you have, let's say, times 3, right? Clearly there's a number missing there. What do you do? Well, you just check if, so this is the first thing that gets called. So expression node, we parse the expression node leave, right? Which is going to be this binary operator here. This binary operator, well, we can just continue parsing that binary operator because binary operator node right here expects us to pass in the left-hand side of the expression. Well, we don't have a left-hand side, just pass in null, right? And then continue with the precedence of this operator. This is why I'm calling getTokenPrecedence right here. And continue parsing the expression as if nothing happened, right? And then later on, when you walk the tree, you will encounter a multiply node, right, for a binary expression, and then you suddenly realize, well, the left-hand side is 0, so a null pointer, so it's missing. So then you can report an error saying, hey, left-hand side of the expression is missing, right? Okay, what about things like 3 times 4, right? Something like that. Well, we pass the left-hand side, which is just an immediate, that's fine. Then we go into the binary operator node right here, because, you know, we have a binary operator. And then we try to pass the right-hand side. Well, this is the right-hand side here, right? So this is the right-hand side. What happens on this right-hand side? Well, I just explained it previously when we had the times 3. We just return a binary operator node with an empty left-hand side. Okay. So then this would basically, this would return a tree that is basically binary multiply with the left-hand side of 3, and the right-hand side will be a binary multiply with left being empty, right? So 0, and the right being 4. One thing I have not thought about, but let's walk through that scenario. What if this is an AND, right? So this has a lower precedence than this. So if there was a number, what you would want in the end is a binary multiply, right, with left being 3 No. No, yeah, with left being 3. And hang on. You would want... No, you have this one with left 3 and the right being this one, right? Which in return has a left of 3 and a right of 4, right? And then we have the other way around, so we have 3 times 3 and 4. He would want to end up with and basically the same thing, right? With left being this, which in turn is left 3 and right 3. And here the right would be 4. Okay, so that is the tree that we want, right? So now let's pretend here the number is suddenly missing, right? So what would we do? We parse in the 3, we have a binary operation of this one, right? And then we try to parse the right-hand side. The right-hand side encounters this, so we just pretend it's a binary that has the left-hand side missing. So we would end up with the same tree. Okay, cool. So what if this happens? So this would generate a invalid tree. Because now the right-hand side of the multiply, so the multiply would be the first one, and then, okay, so I need to take operator precedence into account of the previous Okay, this might have to go outside because it relies on precedence, right? So really what you want is Okay, realistically, really what you want is just to leave to be 0, right? So I can remove this check. You want the leaf to be 0. And then let's see if this is 0. Doesn't really matter. Okay. But then this kind of breaks what I wanted to do with these things, so with the open bracket and separators, so I need to rethink this part a little bit. Okay, but those are binary operators. Okay. Calls binary operator with empty left-hand side. So, and unary operators are a bit easier because let's say we have minus, right? All we need to do is then call expression node, but with the highest possible precedence. Yeah. Okay, cool. So let's do that. Unary operator. So we have this one. As you can see with unary operators, I had like this whole chat of like, okay, what are valid tokens, right? And then it calls like only these things, and then I have all the errors for like invalid tokens, and like the code just grew massively. But now we can just remove that. So, unary operator. The unary operator just has a type and then the syntax value, so which will just be another expression, which you have to do because, you know, you could have minus and then suddenly braces, right? Like something like this. You want to negate the whole result of, well, you want to go out. Okay, I have to let the dog out of the room. Hang on. There you go, my lady. Gets annoyed when I talk, I guess. So, basically do the same thing as in the binary operators. I just allocate a unary operator, assert that the result is not 0, and then have the result type, which is just the token type. That is cool. Then we need to advance to the next one. And then result value really just becomes an expression node, right? So we go back into here, and we're calling it with Alexa and token precedence max. So a unary operator node, it's just this, right? Here we can just say result data is this, right? See, and then when I was returning invalid nodes for like potential errors, I was then like, okay, maybe I can squash like a whole tree that just has one invalid node. I can all squash it down to just a single invalid node, right? And then like to save some space or whatever. But that also made the code more complicated, right? I was going down into this whole rabbit hole of like, oh, it was just basically a mess, right? So return result. It'd be nice if I know how to spell return. I need to sit properly. Okay, is node unary operator, right? Okay, this is still right. And then we just get the node data like so. Okay. So really, all we need to do now is here, if we have a unary operator, we don't even need to advance because that happens inside of inside of here. So we just say unary operator node. Turn unary operator nodes token. Calls expression node with max precedence. Okay. Now brackets, right? I have open bracket nodes and close bracket nodes. And all they have is a type that specifies, you know, I'm a round or square open bracket, and this one says I'm a come on. I'm a close, a round or square close bracket. Jesus, my brain. And then I have this brackets type here, and that just takes in the open bracket node, the close bracket node, and then the expression in the middle, right? So if I encounter an open bracket of either type, I am going to create an open bracket node of that type, advance the Alexa, try and read the expression with minimum precedence. So because we're restarting the whole operator precedence, right? Because this is a sub-expression, it's in brackets. And then if this returns, I need to check if the token, the current token, is a close bracket. If it is, I create a close bracket node of one particular type. Doesn't matter what kind of close bracket it is. Because again, parsing that it is the correct one is not part of the tree generation, right? That will happen one step out of this. If we have a close bracket node, we just advance the lexer to the next token, right? If that token is not a close bracket, we just set the close bracket to 0, which means we are missing a close bracket. But now, in before, I was ignoring close brackets here and as an expression node leave, and kind of leaving it up to the calling code to handle those. But since 0 now is officially saying, hey, something is missing, I might not be able to do that anymore. I have to have a think about this. And luckily an ad break starts in like 1 minute or so. So this gives me a little bit of time. I don't know why ads are so frequent now. I guess not really frequent. It's been 30 minutes. Man, time flies. Jesus. Okay, well, I see you after the ad break, and I'm gonna think about this while this happens. If you can still see me, I still will be very quiet, because I'm thinking about this now, so... Pen and paper. Let's get going. Okay, ad break should be over. And so... there's a few ways to do this. for one, I can just return the empty bracket. Okay, let's think about this situation, right? 1 plus 2 times 3 plus 1. And I'm missing a bracket, right? So just trying to get some scratch field here. Okay. All of these restart the expression parsing with the highest precedence. That is okay, right? So this one would result in a plus node with left okay, let's just boil this down to this. Right, so this one would work, left, right, 2, right? And then because we're restarting the expression, this would be the left-hand side of the multiply, right? So this would be something like this. Right, okay, fine. And then right would be that. Okay, these situations would just work because in the brackets code, I'm just checking for the next token whether it is a close bracket, right? And then either it's missing or it's not. It could be a wrong one, but that doesn't matter to us, right? Although it kind of does matter. Because what if we have this situation, right? This one. This would say we have a close bracket. And really the calling code of expression, so that would be something like, what I want in the end is expression next, right? And next will be another expression, right, which has another next. So basically a linked list, right? A linked list of expressions. That's how I can treat separators. Ooh. If I have a separator, I just return a separator expression and then call hang on. I have to think about this. Okay, let's forget brackets for now. I need to think about this a bit more, and it's kind of doing my head in. But separators, I think I can do. So we're doing the left-hand side. It's like unary expressions, essentially. Except it kind of isn't. So we have 1 plus, comma. Okay, so token binary operators, just called empty, and then binary operator node, right? Here we have a separator node. Which means whatever I was doing before is now done. So really, what I want to return is just the leaf, because anything else will be part of the next expression. Could that call it? I suppose it could. So really, what are separators, right? They're just, they have a left-hand side and a right-hand side. Left could be empty, comma, right? And or left, comma, empty, right? Left, right without a comma, well, that is a entirely special case. Except it kind of isn't. Operand node, right? Lexer T, Lexer. Okay. Operands. What is an operand? I had this as expression next. But really, I have to watch out for the separator. So left, separator, Could just be a flag, honestly. And next then becomes another operand which has a left-hand side, a separator, and a right-hand side. Is separated, right? So something like this. So that means we have operand T, operand. Okay. Operand result, get memory arena type, Lexa arena of operand T. Simple assert. All these asserts are just a solution to a temporary problem. I can remove those later on because really these get memory arena functions should always return valid memory. If we ever run into a situation where they can't, then I'm just gonna kill the process because something horribly went wrong then, and then we need to stop anyways. So, yeah. So results. So we have a left-hand side, right? Which is an expression node with token precedence min. If is token separator, Lexa current token, then Lexa advance and say result. Actually, result is separated. Right, and if result is separated, then we advance. Result it's basically similar to a binary operator, really. And now I'm wondering. Dude, I could just make that a binary operator. Would that be hacky? I mean, comma is kind of special here, but nah, I'm not gonna make this binary operator, no matter how similar they are, right? I'm just gonna let's not go down that route. Okay, and then we have the right-hand side, and that will be another operand node. Okay, and then operand node will just be syntax node, result, new node, lexer. Oh, I just need lexer, and then syntax node type separator. I need to make sure I have a separator. Right, cool. No, operand. What am I talking about? It's operand. Right. And then results data is operand lexer. Return result. Right. And then we can have helpers, such as these. Is node operand get operand value, and then is node operand, and here we return the operand value, right? So like this. Okay, so this is like the top level thing, right? So we're passing an expression node, whatever it is, we're checking the next token separator, right? To mark whether it is separated or not. Then we just pass in the right-hand side. Now let's assume we have an operand that's like empty, right? There's nothing there. This would result in a empty expression node. This would result in false, it's not separated, and the right-hand side would result in an empty expression again. Now, situations like comma, okay, so that would be that. This is perfectly valid. Okay. Now, if we don't have a comma, so not a separator, this will just be false and we don't advance and we just read the next expression, right? And then when we pass the tree, we can be like, okay, we have a right-hand side of our operand, but we don't have a separator. Clearly that is a syntax error, right? So we can deal with that. Now, what if is empty, but now we have a comma, right? How do we terminate with a comma? I think there's no way around to have some more checks right here, right? So, okay, leave, right? Leave can be 0, which is a perfectly valid thing to do. But then if it is a separator, we don't go back in here. Well, we don't need to. Yeah? What's up? Okay, I have to stop the stream. We had an accident in the family, so bye.